If the entire shipment of parts has a very high level of defects, we hope the sample will reflect that fact with a very high probability of rejecting that shipment. So why OC? Firstly, the curve indicates the discriminating power of the acceptance plan. Secondly, it helps in selection of plans that are effective in reducing risk. And lastly, it helps to keep the costs of inspection down. So there are two types of OC curves. The first type, type A, gives the probability of acceptance for an individual lot coming from a finite production, whereas type B gives the probability of acceptance of lots coming from a continuous or infinite size lot. The most common and the one we will be focused on today will be the type A OC curves. So these are some of the variables to be considered. We have the capital N, which is the total lot or batch size, lowercase n, which is the sample size, C, which is the acceptance criteria or what the standard is, and lastly, PA, which is the probability of acceptance of the lot. And I want to go more into depth on the C value. So here are some samples we have taken from our population. We can see that two of these samples have non-conforming units in them. Let's say we're dealing with a sampling plan with a C value of 2. We can take any of these 4 samples and would be able to accept our lot. But if we have an acceptance criteria of 0, then we can only accept the 2 without the defects. So these 2 over here. So the ideal OC curve. As you can see, the x-axis is the actual percent effective, and the y value is the probability of acceptance. So this figure shows a perfect discrimination plan for a company that wants to reject all lots with more than 2.5% effectives and accept all lots with less than 2.5% effectives. Unfortunately, the only way to have 100% acceptance of good lots and 0% acceptance of bad lots is through full inspection, which can be very costly. So in reality, no OC curve will be step-like like this one. So let's take a look at a more realistic OC curve. Here are some sample OC curves. So our sample size is either 50 or 100 in these, and our acceptance criteria is either 0 or 2. You can notice how the shape changes based on the sample size and the acceptance criteria. With the red line, the acceptance criteria is larger, and so we have a higher probability of acceptance. Let's take 1% non-conforming in population as an example. So 1 out of 100 units have something wrong with it. If we look at the red plan, it has a guarantee that we will accept our lot here. So 1%, almost 100% of probability of acceptance. But if we look at the blue curve with an acceptance criteria of 0, so this one over here, we can't have any defects in our sample. So that means we have a 35% chance of accepting our lot. So only 35 out of 100 lots are going to pass inspection with that tighter criteria. So what are some properties of OC curves? There are basically 2 golden rules to remember for OC curves. Firstly, the higher the sample size, the lower your probability of acceptance will be. And secondly, the higher the C value, the higher the probability of acceptance. And we can see this in further detail in the next slide. So as you can see here, the first figure, the higher the sample size, the lower the probability of acceptance. And this is because you're likely to scoop up a defective product if your scoop is bigger or if your sample size is bigger. So hence, you have a lower probability of acceptance. And then the lower image, we can see the higher C value gives the higher probability of acceptance. And this is because you can have more nonconformities and still accept your population or lot. So there are a few ways of calculating OC curves. Firstly, we have binomial distribution. Secondly, we have hypergeometric distribution. Essentially, the probability that our defects are found in a sample of n. And lastly, Poisson distribution. So OC curve calculation by Poisson distribution. The Poisson formula can be used to calculate an OC curve. And essentially what it gives you is the probability of exactly R defects in n. And there is one limitation of using Poisson for calculating OC curves, and that is your n, which is your sample size, has to be less than or equal to your total batch size divided by 10.